This is module 4, repeated measure. Using repeated measure ANOVA, we can answer if there is any mean differences among the groups when the response variable is repeatedly measured on those groups. The most of the classwork is based on the Data Novia website. Suppose we wish to know if regular hot yoga practice shows a significant weight differences. There are 10 participants, Amy to Wyatt, participated in the program, and their weight is measured repeatedly at week 0, 2, 4, and 6. The table at the bottom shows a structure of the data. The research question is if there is any mean weight differences among different weeks. Here, the independent variable is the time, which represents the column of the data, and the dependent variable is the weight, which represents all the values in the table, data table. Notice that if we focus on only week 0 and week 6, this is paired sample t-test. We can compare before week 0 and after week 6 and see if there is statistically significant difference in weight. Also, if we ignore the dependency of the data, meaning ignore the fact that each row is for the same participants. This is identical to one-way ANOVA, comparing mean weights for week 0, 2, 4, and 6. So hypothesis test for repeated measure is conducting all the group means are the same versus alternative hypothesis, which is at least one of the mean is different when, again, the response variables are repeatedly measured. Let's see ANOVA table for the repeated measure. Recall that in one-way ANOVA, there was 2 error sources. One from the group, so called between treatment, and the error within. And these 2 make the total variation. The sum of squared total is sum of the squared between groups and the error. If the repeated measure, in the repeated measure, we have an additional source of variation between subject variation. Thus, sum of squared total is sum of the squared of between groups or between treatment. Sum of squared between subject, SS sub, and the error. And if you add SS sub, SSB, SSW, that will actually make SS total. This makes an additional row right here between subject and ANOVA table. Note that N is a subject, number of subject, and K is number of groups. The degree of freedom of between subject is the number of subject minus 1. The degree of degrees of freedom of between groups is the number of groups minus 1. The degrees of freedom of total is always the total number of data minus 1, which is N times K minus 1. So when we know N minus 1, K minus 1, and NK minus 1, if you add all the degrees of freedom, just like a sum of squares, if you add degrees of freedom of between subject, between treatment, or between groups, and the error, it should be total of the degrees of freedom of total. So if you do a little bit of algebra, you will figure out that the degrees of freedom of the error will be N minus 1 times K minus 1. Mean squared errors are sum of squares divided by the degrees of freedom, corresponding degrees of freedom. MSB is SSB divided by K minus 1. And MSE is SSW divided by N minus 1 times K minus 1. F is MSB divided by MSE, and corresponding p-value will be on the ANOVA table as well. Note that SSW1, recall the error, the SSW1, the error in a one-way ANOVA. And as you can see right here, the SSW1 in one-way ANOVA is becoming SS sub plus SSW, because SSB is exactly the same here. Since by the definition, the sum of squared value here, SSB, SS sub, SSW are all positive value, and SSBs are the same. When SS sub is positive, you can kind of tell that SSW1 is larger than SSW. The same way, meaning SSW, which is the error sum of squared in repeated measure, is smaller than error of sum of squared error in one-way ANOVA. This actually often make MSE in repeated measure is also smaller than MSE in one-way ANOVA. Okay, so it depends on degrees of freedom a little bit, but if SSB is a decent amount, SSW will be substantially smaller than SSW1. And then once you divide by degrees of freedom, often MSE in the repeated measure is smaller than MSE in one-way ANOVA. This leads, since MSE is smaller in repeated measure, this will lead the larger F value, F test statistics value in repeated measure, and often is more likely to reject the null hypothesis. In other words, it is often more powerful compared to one-way ANOVA and more likely to find mean differences. Okay. Let's formally write the hypothesis of the repeated measure ANOVA. The null hypothesis is all means for the different groups are the same. The alternative hypothesis is that at least one of the means is different from the rest. F test statistics is MSB over MSE, and we reject null hypothesis if F test statistics value is larger than F table value, or p-value is less than the significance level alpha. This is the end of the first video.